This is problem number 72 on page 43 of chapter 2 of the textbook. It reads, two children are playing on two trampolines. The first child can bounce up 1.5 times higher than the second child. The initial speed of the second child is 5 meters per second. Part A asks, what is the maximum height the second child reaches? I've made a quick sketch here for you to use, and I recommend actually making sketches like this. I think that you'll find that the problem is actually much easier than it appears to be written in the problem, since no sketch is given. So the first question is finding the maximum height of the second child. Let's go ahead and write down what we know. We know that the initial velocity is 5 meters per second. We also know that the acceleration due to gravity is going to be negative 9.8 meters per second, and we know that because the child's jumping on Earth, and anything that's only being acted on by gravity will accelerate in such a way. We can say that the initial y position of the child is equal to 0, and we'll basically be looking for the final y position. There's an additional piece of information that we know. Technically speaking, by the way, y final minus y initial is delta y. We don't know what that is, and really that's what we're looking for. And finally, we know that the final y velocity of the child is going to be 0 at maximum height. So with those initial conditions, we can basically pick one of our equations of the three kinematics equations to choose from. It makes sense in this case to use the third equation. Vf squared is equal to Vo squared plus 2a delta y, where everything is known except for delta y, but that is what we're looking for. Okay, so I'm going to subtract V naught from both sides. I get Vf squared minus V naught, or V initial squared, divided by 2a is equal to delta y. Notice that my final is 0, so that becomes 0 minus 5 meters per second, and then I have to square that whole quantity, divided by 2 times negative 9.8 meters per second. Once I do that, I can arrive at a displacement. I'm going to have a negative 25 in the numerator and a negative 19.6 in the denominator, and for part A I get 1.276 meters. Truncating for significance, I would call that 1.3 meters as my answer, the one that I would communicate on a summative for delta y. Okay, that's part A. Part B then goes on to ask another question. Part B says, what is the initial speed of the first child? So let's go ahead and take a look at our sketch. We don't know what the initial speed of child number 1 is. It's not given to us in the problem. However, we do know indirectly what delta y is. It's 1.5 times the height that we just found in part A. Let's go ahead and write our initial conditions. V initial is what we're looking for, and this is for child number 1. I could, if I wanted to, put subscripts of 1 here to denote child number 1, but that's fine. We know that V final for child number 1 is going to be 0 at max height. We know that delta y for child number 1 is going to be positive, and it's going to be 1.5 times the 1.276 meters that we just solved for in part A. When we multiply that, we get 1.913 meters. So we know that child number 1 is going to be 1.5 times, or 50% higher than child number 1, which gives us 1.913 meters. Finally, we again know that the acceleration is a constant for anyone that is only under the influence of gravity, and we get negative 9.8 meters per second. Again, we see that the third equation is the one to use, so I'm going to go ahead and do the work here. I'll say that Vf squared minus Vo squared is equal, Vf squared is equal to Vo squared plus 2a delta x. In this case, I'll use delta y, of course, since I'm talking about vertical displacement, and we are going to solve for V naught, which is the initial velocity. That becomes Vf squared minus 2a delta y is equal to V naught squared. I'll need to remember to take the square root of both sides, and so my expression for the initial velocity of the first child is the square root of Vf squared minus 2a delta y. Let's go ahead and substitute some numbers in now into that expression. My final velocity is going to be 0, so 0 squared is 0, of course, minus 2 times negative 9.8 meters per second per second. And let me go ahead and extend the radical here, and my vertical displacement delta y is a positive 1.913 meters is equal to v naught. Once I run that through my calculator, I get about 6.1 meters per second is going to be the initial velocity of child number 1. Okay, part C then goes on to ask the question, how long was the first child in the air? There's a couple of ways to solve this. You can do it in kind of a few different ways. I would draw your attention here to the symmetry of this path. So the child is going to go up, and then at that point right there, that's going to be half of the total time. If we're ignoring air resistance, we can say that the child comes back down and therefore reaches the trampoline, the surface of the trampoline, with the same 6.1 meters per second in the downward direction with which he left it on the way up. Okay, so those are things that we know. Let's go ahead and solve the remainder of this problem in the space here underneath. I'll solve it part C in green. Okay, so what do we know? Again, as usual, we know the acceleration is going to be negative 9.8 meters per second. We know the initial velocity of child number 1 now. We've just solved for it. It's an upwards 6.1 meters per second. And we know the final velocity of child number 1 at maximum height. It's 0 meters per second. We can solve then for the time that it takes child number 1 just to get to Vmax. That's not the total time that it takes the child to come all the way back down. That would be 2 times whatever time that is. So this basically analysis using the second equation Vf, oops, there is no square there, so let me get rid of that. So we're going to basically use Vf is equal to Vo plus acceleration times time, and let's solve for time. Vf minus Vo divided by acceleration is equal to time. My final velocity is 0, my initial is 6.1 meters per second, and I'm going to divide that by negative 9.8 meters per second per second. That's going to give me a time of 0.622 seconds, but that's only the time that it takes to get all the way up to max height. I would need to multiply that time by 2 to get our final answer, which is going to be about 1.2 seconds for the child number 1 to get all the way back down.